So what we looked at last day is the idea of list comprehensions. And what we saw is that these give you a very simple but a very powerful way of programming with lists in a language like Haskell. So what we're going to be looking at today is the idea of recursive functions, which, as we'll see, is one of the key topics on this course. So as an introduction to this, as we've seen, many functions can be naturally defined in terms of other functions. So here's a simple example of this. Here I'm defining the familiar factorial function, which takes a single integer and gives back a single integer. And in mathematics, the factorial of a number is simply the product of all of the numbers between 1 and that number. So for example, the factorial of 5 is the product of the numbers between 1 and 5. And in Haskell, this has a particularly simple definition in terms of two other functions. So the definition here says the factorial of any number n is simply the product of the list from 1 up to n. So here I'm using two built-in functions, one called dot dot, which builds a list between any two given numbers, in this case 1 and n, and then that list is being passed as the input to the product function, which simply multiplies up all the elements. So a very simple idea. Many functions can be naturally defined in terms of other functions, and this is how you could define the factorial function like this. In fact, in a language like Haskell, there is many different ways that you could define the factorial function. And actually what I'd like to show you quickly is a blog post which talks briefly about this. So this is the blog post which I wanted to show you. It's called The Evolution of a Haskell Programmer, and it's by a friend of mine, Fritz Ruhr from Willamette University in the United States. And what Fritz is doing in this post is he's showing you a whole range of different ways of increasing complexity that you could implement the factorial function in a language like Haskell. So at the start you have your freshman Haskell programmer, then you have your sophomore Haskell programmer working at MIT who likes lots of brackets, then you have your junior Haskell programmer, and it goes on and on. There's many different definitions for the factorial function, and they rapidly get quite complicated. So here as an example, using what's called combinatory logic to implement the factorial function, and it goes on and on and on, and it gets down to kind of graduate level stuff, PhD level stuff, and so on. And if I scroll right down to the end, after about 20 or more definitions, we will find the simplest definition which there is for the factorial function, which is this one here, which we have just been looking at. The factorial of n is the product from 1 up to n. And that's the tenure professor version, which is me, teaching Haskell to freshmen, which is you. So again, just for a bit of fun, you might want to have a look at this blog post and see a whole range of different ways that you might implement a function like factorial in a language like Haskell. So returning back to the slides now, something we haven't really talked about very much in the course so far is how expressions are actually evaluated in Haskell. And this is by a very simple stepwise process of simply applying functions to their arguments. This is the hallmark of a functional programming language. Computation proceeds by simply applying functions to their arguments. So let's have a simple example of this with a factorial function. So what I've made for you here is a little animation. So we're trying to work out, using our definition, what is the result of computing the factorial of 4. Well, the definition says the factorial of any number, like 4, is simply the product of the list from 1 up to that number. So in our case, if we apply the factorial function, we're simply going to get the product from the list 1 up to 4. And now what do? Well, we've got two functions now. We've got the product function sitting here applied to the list between 1 and 4. And that is the dot dot function here. So what are we actually going to do to proceed? Well, we can't apply the product function yet because we don't actually know the full extent of that list. So we need to apply the dot dot function first to actually expand the list out to 1, 2, 3, and 4. Now we can apply the product function, and we'll see later on today how you can define that itself in Haskell, in fact recursively. So if you take the product of the list 1, 2, 3, 4, you'll get simply 1, 2, 3, 4, and then finally you do the multiplications and you get the result 24 at the end. So this is the process of applying functions to arguments to evaluate an expression. What I'm often going to refer to this is as turning the handle. So you kind of turn the handle with a function definition and you see what it produces in the end. And we'll see many, many examples of kind of turning the handle with function definitions like this in the course. So now let's move to the main topic of today, which is the idea of recursion. So in Haskell, functions can also be defined in terms of themselves, and that's what it means to be recursive. So a recursive function is simply one which is defined in terms of itself. And here is one possible definition for the factorial function using recursion. And we've got two equations here, or two cases. The first one is called the base case, because it's actually going to stop the recursion. And the second one is called the recursive case, because it's defining the factorial function in terms of itself. So let's have a look at the two cases. So the base case, the first equation, simply says the factorial of 0 is 1. Okay. The second case says the factorial of any other positive number n is going to be n times the factorial of its predecessor. So what you can see here is if you apply this function to a number like 5, it's going to say the factorial of 5 is 5 times the factorial of its predecessor, which is 4. So each time this recursive function calls itself, the parameter is going to get 1 smaller until it eventually reaches 0, and then you will get back the result 1. Okay, so simple two-line recursive definition, one base case, factorial of 0 is 1, and one recursive case that says the factorial of any other number n is n times the factorial of its predecessor. And just a little technical point to make here, when you're defining recursive functions on non-negative numbers, such as this one, you typically have these two cases here. So you have a case for 0, which is typically your base case, and then you have a case for n, which is going to be typically your recursive case. So 0 and n are the standard patterns when you're defining recursive functions on non-negative numbers, or natural numbers, if you like. They're not always the patterns which are appropriate, but in many cases they are. So let's see a simple example then of turning the handle with this definition. So let's work out from first principles what is the factorial of 3 according to this definition. So the definition says if you've got 0 you get 1, so we don't have 0 in this case, so we need to go to the second equation. And the second equation said the factorial of any other number n is n times the factorial of the predecessor. So in this case n is 3, so we're going to get 3 times the factorial of 2. And now we think, well, what do we do now? Well, we can't do the multiplication because we don't know what the second parameter is, but we can apply the factorial function again. So we just apply the factorial function again. What is the factorial of 2? We turn the handle, that's 2 times the factorial of the predecessor, which is 1. So factorial of 2 works out to be 2 times factorial of 1, and we just copy down the 3 times from the line above. And then we do the same thing again. What is factorial of 1? Factorial of 1 is 1 times the factorial of 0. And now we're down at the point where the recursion can stop because we have factorial of 0, which is our base case. And factorial of by 0 is by definition 1. That's what we defined it to be. So we can say factorial of 0 is 1. And now we can start to do the multiplies. We do the other one first. 1 times 1 is 1. Then the 2 times 1 is 2. And finally, the 3 times 2 is 6. So this is turning the handle with this definition, just applying the factorial function until we get down to the base case, and then we can start to do the multiplications. So if you're a C or a Java programmer or an imperative programmer, you may look at something like this and think, well, this could potentially be very inefficient, because if you look at the structure of what you're building up here, you're building up a very large intermediate computation with loads of kind of suspended multiplications, which then in the final point, once the recursion stops, you actually do. But the message here is the same one, which I've said again and again. You write clear, concise, correct programs, and you let the compiler worry about making them efficient. And it's very often able to make them efficient. So actually kind of writing highly efficient programs is not something we're going to worry too much about in this introductory course. I just want you to learn how to write very simple, short, elegant Haskell programs and let the compiler worry about efficiency for you. So a couple of points to note here. The first point is, why did we define the base case to be factorial of 0 is 1? And this is appropriate because 1 is the so-called identity or unit for multiplication. If you multiply any number x by 1, it doesn't change it. So if you wanted to be precise, as in the top of the slide here, 1 times x is x, and x times 1 is x. So that's the appropriate base case for this definition. Another important point to note is that the recursive definition for the factorial function diverges if you give it numbers which are smaller than 0, because the base case is never reached. The base case says factorial of 0 is 1, the other case says factorial of n is n times the factorial of the predecessor. So if you give this a number like -1, it's just going to say -1 times the factorial of -2, and then it's going to say what's the factorial of -2, and you can see it's just going to recurse forever. So we could say, if we wanted to be fancy, we can say it diverges, which means that it just doesn't terminate if you give it numbers smaller than 0. In the example here, you might think, well, why did I need the brackets around the -1? And that's simply because if I wrote factorial and then a minus sign and then a 1, it would think I was trying to subtract 1 from the factorial function. So it would interpret the minus sign as an infix minus operator. If you want to have a negative number like -1 and you want to pass it into something, then you need to put brackets around it like I've done here. So we can ask ourselves now, why is recursion actually useful? So I've put together a few observations about this on the slide here. So the first point is that some functions, such as the factorial function, are simpler to define in terms of other functions. If I was to define factorial, I would do it exactly as we did at the start of the lecture today. I would simply say the factorial of n is the product from 1 up to n, using the product function and the dot dot function. And as we saw, that was the final and simplest definition in the blog post that we had at the start of the class. As we'll see, however, many, if not most, functions can naturally be defined in terms of themselves. And if you've done lots of imperative programming before, you might think, well, it's actually not very natural to think in terms of recursion. But what we'll see is the more recursion you see, the more this becomes a very natural way of thinking. And one of my aims with this course is to get you being very comfortable with recursion, so that you can have it as a kind of standard tool in your toolbox, no matter what kind of programming language you're using. And the last point here is an important one. If you define your functions using recursion, then you get one of the mathematician's most powerful tools, which is called induction, to do mathematical reasoning or proofs about your programs. So this is not something we're going to see terribly much of, or really anything of, in this particular introductory course, but if you take the advanced functional programming course with me in second year, we'll be seeing quite a lot about how to use induction to prove useful properties of your Haskell programs. So what we're going to do now is think about recursion on a different data structure, and we're going to think about, in particular, recursion on lists. So the observation here is that recursion is not just restricted to numeric things, to numbers, but we can also use it to define functions which operate on lists, and that gives us some flexibility to define lots of interesting functions. So here, for example, is how we could define the product function, which we used in the definition of factorial. And it's got 3 lines, so let's consider these 3 lines one at a time. So the top line is the type, and it says for any numeric type A, then product is a function which takes a list of A things and gives you back a single A thing. So I've made the function product here flexible. It can take a list of integers or a list of floats or a list of doubles, any kind of numeric things. It can multiply them together, but it can't, for example, multiply a list of characters because the char type is not in the num class. So that's everything we need to know about the type. And then the definition has 2 cases. We have a base case, which here is the empty list, and we have a recursive case, which is here a non-empty list. And in the base case, all we're simply saying is if you take the product of a list with nothing in it, we're going to get back the value 1. That's where the recursion is going to stop. And the recursive case says the product of any non-empty list whose first value is n and whose remaining values are n's is simply the first value n times the product of the remaining list n's. Okay, so a nice simple 2-line recursive definition, 1 base case and 1 recursive case. And just as we have standard patterns when we're defining functions on numbers, the first thing you typically try is 0 and n as your patterns. When you're defining functions on lists, the first thing that you try is the empty list and non-empty lists, and see if that will give you a good way of defining your function, and often it does. So these are the kind of the standard patterns for lists. You have an empty list case and you have a non-empty list case as well. So let's make sure we understand how this definition is actually working. Let's turn the handle again with a simple list. So let's work out what the product of the list 2, 3, 4 is from first principles just by applying the definition. So we have a non-empty list here, so we need to go straight to the recursive case. And the recursive case says if you've got a non-empty list, the product of that list is the first thing, in this case 2, multiplied by the product of the remaining list, which in this case is 3 and 4. So if we turn the handle once, we get 2 times the product of 3 and 4. And then we think, well, we've got 2 functions at play now. We've got the multiplication operator, but we can't apply that yet because we know what its first parameter is, it's 2, but we don't know what the second parameter is. But then we can think about applying the other function here at play, which is product. So we just apply the function again. So what is the product of a non-empty list comprising 3 and 4? Well, all we're simply going to do is take the first thing in the list, which is the 3, and then multiply it by the product of everything else, which is the 4 sitting in a little list on its own. So if we turn the handle again, we get 3 times product of 4 sitting on its own, and we just copy the 2 times down. Then we just do the same thing again. What is the product of a singleton list with a 4 in it? Well, it's just the 4 times the product of the empty list. Now the recursion has stopped. We have the base case. The product of the empty list is 1. And then we can do all the multiplies and we get back the final result, 24. Okay, so you see now why we made the base case 1 rather than 0, because 1 is the unit for multiplication, so it doesn't have any effect on the multiplication. If we said the product of the empty list is 0, in the second last line, everything would then collapse and we'd actually get the result 0. So you need to think very carefully about your base cases, otherwise you can often end up getting completely the wrong result or even collapsing the result down to something meaningless. So using the same pattern of recursion as product, we can actually define many other useful functions. And in particular, for example, we could define the length function on lists. So just a small technical point here, the pattern of recursion we're actually using here is something called primitive recursion. This is a very common pattern of recursion on lists, and we'll see more about this later on in the course when we come to think about higher order functions in lecture 7. But for now, let's just think about how we can define the length function. So here's a simple 3-line definition for length. The type is very straightforward. We're simply taking a list of A things. It's polymorphic because we don't care about what the elements are when we're computing length. And then we give back a single integer. And as before with the product function, we have a base case, which is the empty list, and we have a recursive case, which is a non-empty list. So in the base case, this is very easy. If I give you a list with nothing in it, the empty list, there's nothing to count, so we give back the value 0. If I give you a non-empty list, what we're going to do is count 1 for the first element, and then we're going to recursively calculate the length of everything else. And you might think, well, what's the underscore on the left-hand side? Well, remember, that's the wildcard character. Notice that we don't need the first value in the list. I could have called the first value in the list x in the pattern x colon x's, but we don't need the value of the list, the value of the elements when we're actually calculating the length of a list. So I don't need the variable x. So I can make it clear in the definition just by having a simple underscore here. Makes the definition easier to read. So again, we can just turn the handle with this definition to make sure we understand actually what's going on. So what's the length of the list 1, 2, 3? Well, it's a non-empty list, so the recursive case applies, and we simply get 1 plus the length of the tail of the list, which is 2 and the 3. And then we just do the same again. We can't apply the addition yet because we know what the first parameter is, it's a 1, but we don't know what the length of that list is. So we then just proceed to turn the handle again and calculate the length of this list. So what's the length of the list 2, 3? Well, we simply take a 1 again, plus the length of the tail of the list. So that's 3 in this case. And then we just turn the handle one more time. What's the length of the list with a 3 in it? Well, it's simply 1 plus the length of the empty list at the end. Now the recursion stops, the length of the empty list is 0, and we can do all the additions, and we finally get back the result 3. So again, nice simple 2-line recursive definition using the pattern of primitive recursion on lists that we'll talk more about later on. So just as another example to illustrate the same kind of idea, using the similar pattern or a similar pattern of recursion, we can also define the reverse function, which is a bit of a more interesting one here. So again, it's a 3-line definition. So reverse takes a list of things and gives back a list of things. And the recursive definition says in the base case, you reverse the empty list, you simply get back the empty list. Okay, very simple base case. We don't really need to think about this one. So then we can think about the recursive case. What's actually going on here? Well, imagine I gave you a list like 1, 2, 3, 4, and I asked you to reverse it. One way you could do this is you could take the tail of the list, which is 2, 3, 4, you could reverse that recursively, and that would give you 4, 3, 2, and then you could stick the first thing, the 1, on the end, and that would give you the 4, 3, 2, 1. So that's a way to recursively decompose the problem of reversing a non-empty list, and that's exactly what's expressed in the recursive case here. We're simply saying if you want to reverse a list where X is the first thing in the list, X's is everything else, then you reverse the everything else, so you reverse X's, and then you put the X on the end in a little list on its own. And notice here I need to make X into a singleton list because I'm using plus plus, which takes 2 lists as parameters. So reversing X's is a list. X on its own is just a value of type A, so I need to make it into a list of things, so I put the little list brackets around it, make it into a singleton list, and then I can actually do the append. So let's have a simple example of this one, just to again bring home the point about what's going on and make sure everyone's following how to execute these things and how these recursive definitions actually work. If we reverse the list 1, 2, 3, what we do is we go to the recursive case, we reverse the tail, which is reverse of 2 and 3, and then we put the first thing on the end in a little singleton list on its own. Then again, what do we do? Well, we just recursively apply reverse. How do we reverse the list 2, 3? We reverse the tail of the list, which is the 3 on its own, and then we put the first thing in a little list on its own. And then again, how do we reverse 3 sitting in a list? We reverse the tail of the list, which this time is the empty list. Then we put the 3 on the end sitting in a little list on its own, and we copy everything else down, and we get all of this stuff in the blue box here. And now, again, we've reached the base case, reverse of an empty list. There's nothing to do, we get the empty list, and then finally we can smash all of these things together. So far, all the functions that we've defined using recursion have taken a single argument or a single input. But of course you can generalize this to multiple arguments, and functions with more than one argument can also be defined using recursion. So let me give you a few examples of this. So the first example is our old friend, the zip function, which we've seen quite a few times now. And zip takes a list of A things and a list of B things and pairs up the corresponding elements of the 2 lists to give you a list of pairs of A's and B's. And the definition is by 3 equations. We actually have 2 base cases this time and 1 recursive case. So let's understand the 3 equations. So the first equation says, if the first list is empty, then we don't care what the second list is because we don't have any elements to zip with, so we simply give back the empty list. The second case is the dual for when the second list is empty and we don't care what the first list is, and again we're just simply going to get back the empty list. And then the work of the function is done in the recursive case where we're matching on the non-empty list x colon x's and another non-empty list y colon y's, and we know both of these are not empty at this point because the first 2 cases catch the case where either or both of the input lists is empty. Then if we have these 2 non-empty lists, what we're going to do is simply pair up the first value from the first list, so that's x, the first value with the second list, that's y, and then we simply continue by zipping the remaining lists x's and y's together. Again, if you don't think you understand this definition, do a simple example with it and just turn the handle and see how it works out. So maybe zip the list 1, 2, 3 with the list 4, 5, 6 and see how it actually does the computation if it doesn't make sense. So let me give you two more examples now. So here is the drop function from the standard library, and we've seen this a few times as well in the course. So what drop does is you give it an integer like 5, you give it a list of things, and it will remove that number of elements from the start of the list and give you back everything else. And again, it's a recursive function. It's got 3 cases here. The first 2 cases are base cases. The first case says if you drop 0 elements from any list x's, then there's nothing to do. You just give back the list x's. The second case says if you drop any odd number of elements from a list with nothing in it, you give back a list with nothing in it. And this is a design decision here. If I was trying to drop 5 elements from an empty list, we could have made, or the Haskell designers could have made it just crash or raise an exception, but they chose to make it return an empty list in this case, so that the program doesn't crash. Then the final case simply says if you drop any non-empty or non-zero number of elements from a non-empty list, then you simply drop 1 fewer element from the tail of the list. So if I want to drop 5 elements from a non-empty list, what I do is I drop 4 elements from the tail of the list. Okay, so the elements play no role, or the elements at this point in the definition play no role, so we have again an underscore in the pattern. Again, if the definition doesn't make sense, just try a little example. Try dropping 3 elements from a list with 5 or something like that, and turn the handle and see how it actually works out. So the last example here is an interesting one. This is the library definition for the append operator on lists, which we've been using many, many times in this course. So append is plus plus, it takes a list of A things, another list of A things, and it joins them together to give a single list of A's. And it's got a straightforward recursive definition. It's going to do recursion on the first parameter, the first list. So the first equation says, if you take a list with nothing in it and you append it to any other list y's, then you simply get back y's. Okay, nice simple base case. The second case says, if you have any non-empty list, x followed by x's, and you append it to another list y's, all you're going to do is output the x, and then you're going to recursively continue with the append with the remaining list x's. Okay, so nice 2-line simple definition for the append function, and particularly for this one, I do suggest that you try out a simple example yourself. Try something like appending the list 1, 2, 3 to the list 4, 5, 6, turn the handle on a piece of paper and see how the definition actually works out. So what I'd like to do to end up with today is revisit an example which we looked at right back at the start of the course. Remember when we did the very first lecture, and at the end I gave you a taste of Haskell, and I showed you a program, and I didn't tell you what it did, and then on my iPad we tried to kind of figure out what it did, and in the end we found it was the quicksort algorithm. So this is the point now. We've actually studied all of the things in Haskell that we need to properly understand how the quicksort algorithm works. So let's work through the slide here. So the quicksort algorithm for sorting a list of values can be specified by 2 simple rules in English. So the first rule says the empty list is already sorted. That's going to end up being the base case for our definition. And the second case says, it's a bit of a mouthful, but let me try and say it. So it says non-empty lists can be sorted by sorting the remaining values in the list, which are smaller than the head, sorting the remaining values in the list which are bigger than the head, or the first thing, and then appending the resulting lists on either side of the head value. So if you want to sort a non-empty list, you take everything smaller than the first thing, you sort that, then you take everything bigger than the first thing, you sort that, and then you put the first thing in the middle. So this is the quicksort algorithm specified in English. And what we saw right back in the very first lecture is how we can implement this in Haskell as a recursive definition. So here's the definition which we had. So the type says for any order type A, quicksort takes a list of A things and gives back a list of A things. It's very flexible. You can sort lists of numbers, lists of characters, lists of all sorts of things provided that they're ordered. The base case is just an implementation of the first bullet point, which said the empty list is already sorted, and the recursive case is an implementation of the non-empty list case. So how do you sort a non-empty list? you sort the things smaller than the first thing, you sort the things larger than the first thing, and then you put the first thing in the middle. And that's exactly what's expressed in the non-empty list case here. So we're using list comprehension here in two ways, where smaller is going to be all the values which are in the tail of the list, which are smaller than or equal to the first thing. Larger is going to be all the values in the tail of the list which are bigger or strictly bigger than the first thing, and then we recursively sort both of those and we put the first thing in the middle. So this really brings together everything we've learned in the course so far. It's got a fancy type which is polymorphic and overloaded. It's a recursive function, and we're also using list comprehensions in here to do some list processing. And the point here down the bottom, and it's quite a bold statement, but I actually do believe it's true. This is probably the simplest implementation of quicksort in any programming language. And if you can show me a simpler one than this, I'd be very interested to see it, but I don't really see what you can take out of this program and actually still have the quicksort algorithm. So just to wrap things up then, let's have a simple example to kind of illustrate how this actually works in practice, because this has a double recursion. Note that we're calling the quicksort function twice, once on the smaller list and once on the larger list. So let's make sure we understand how this works in practice. So what I've done on the slide here, quicksort, if I wrote that, the slide wouldn't fit what I want to do, so I've abbreviated it by Q. So what I'm doing here is I'm quicksorting the list 3, 2, 4, 1, 5. So it's the list of numbers in jumbled up order. What do I do? Well, to quicksort a non-empty list, what I'm going to do is quicksort the values in the list which are smaller than the first thing. So 3 is the first thing in the list, so I'm going to quicksort the values 2 and 1, which are the values which are smaller than 3. Then I'm going to put the 3 in the middle, and then I'm going to quicksort the values which are bigger than the first thing, so that's the 4 and the 5. So what I've done is I've decomposed the problem of quicksorting a list with 5 things in it into quicksorting a list with 2 things and another list with 2 things. And then I just apply the function recursively now. How do I quicksort the list 2, 1? Well, I quicksort the list of things which are smaller than the 2, then I put the 2, and then I quicksort the things which are bigger than the 2, of which there's none, so that's the empty list. Then I move across to the other side. How do I quicksort the list 4, 5? Well, I quicksort everything smaller than the 4 in that list, of which there's nothing. Then I put the 4, and then I quicksort the things bigger than the 4, which is just the 5. And now we've got 4 quicksorts down at the bottom line that we need to work out what we do. And it turns out if you sort a list with one thing in it, you just simply get the one thing. And if you quicksort the empty list, you get the empty list. Empty list goes to the empty list. And if you quicksort a list with one thing in it, you get the same thing. And now if you kind of collapse this all down, you will get the list 1, 2, 3, 4, 5, which is sorted. So that's basically all you need to know about recursion, illustrated in a few examples today. What I'm going to do in the next lecture is I'm actually going to switch completely to my iPad and go through the exercises for today's lecture. But what you might like to do before I do that is kind of look through these exercises for yourself and see if you can figure out how to solve them before I show you how to do it on the iPad next time around. So let me briefly talk you through the exercises. So there's 3 exercises here. So the first one is to define a bunch of standard library or standard prelude functions. So for example, I've asked you to define the logical AND function, the concatenation function, and a few others. And they get progressively more tricky. So they illustrate different points. So I would suggest you try and define some of these functions yourself using recursion. And as you'll see, as it goes on, you need to think a little bit more carefully. The last exercises are to do with sorted lists. So we're actually, in the next exercise, we're going to define merge sort. So this is a little helper function. So we're going to be defining a recursive function called merge. And what it does is illustrated at the bottom here. We're taking 2 jumbled up lists. We're taking, 2 sorted lists, 2, 5, and 6. That's in order, that's sorted. And 1, 3, and 4, that's also sorted. And it's going to merge them together to give a single sorted list. So again, this is a very nice example of defining a recursive function which is actually going to work by recursion on two parameters at the same time. So it takes two sorted lists and it's got to merge them together to give a single sorted list. And then the final thing we'll be doing next day, but again, I would recommend you have a go at this yourself before I show you how to solve it, is we're going to be implementing the so-called merge sort algorithm, which is specified in English here, but next time around, I'm going to show you how to implement it in Haskell. So that's it for today. I will see you again next time.